All right, so this is where we were at last time. I hope we get to it because I've taken one of the problems from the textbook and I changed it to about a physics 250 level.
How many, like, if you're good at physics degree, how many levels of physics?
Up through the 400s.
Like, what classes?
Well, let's see. Well, you start at the 200 level with your calculus base. So this class just with calculus. Then your second year, you have electrodynamics, you have advanced mechanics. So take what we did first semester, put it on steroids. So we do that. Then you take modern physics.
Modern physics?
Yeah. So it's physics around new types of technologies like diode technologies, liquid crystals, all that kind of stuff. Now it's starting to get into textbooks, the idea of fusion. Then beyond that, so your next couple of years, you're going to take your thermodynamics, because you guys had a little bit, just a little taste of thermodynamics.
That's like on the path.
Yeah, so there's an entire course on it at like the 300-400 level. And so you do that, you do your quantum mechanics. Trying to remember all the classes I took. You have to take all of your math classes. I took up through differential equations, linear algebra. And usually physics majors will have a minor or a second major. My double major was in chemistry.
There's a lot of physics.
Mm-hmm. But some schools do an advanced level electrodynamics, getting you ready for graduate school, because there's a very classical textbook for graduate school electrodynamics called, the author is Jackson, so they just call it Jackson. And if you don't take the mid-level, it's quite a jump. So
like us doing. Let's just learn something.
But then of course, like most majors, you have to have research.
Yeah.
I did research in holograms.
Like Disney World holograms.
In a way, yeah. All right. Let's see. We have a silver wire. Has a diameter of 2.588 millimeters, contains 5.8 to the 10 to the 28th conduction electrons per cubic meter. A battery of 1.5 volts pushes 880 coulombs through the wire in 45 minutes. Find A, the current, and B, the drift speed in the wire. So what's the drift velocity? Okay, well, for part A, your current is delta Q over delta T. So our delta T you're going to want to convert this 2,700 seconds. Yeah, delta T. Do you think you'll be a contacts person or a glasses person? I found out I couldn't survive in Japan because apparently it's considered a social faux pas and ugly to wear glasses in Japan. So everyone, I can't poke myself in the eye. So I was surprised. I was surprised. They were talking about these social things that people in Japan just don't do, and like glasses is a real no-no. Kind of turns out that they just do that for the rest of the world when they're doing modeling or doing their videos for the internet. That's just kind of like because like some countries like the look of it, so they do it for clicks. But in their yes, it's considered unprofessional.
It's not to not be able to see is unprofessional.
No, I don't know why, but it's considered unprofessional to wear glasses. I was like, that's interesting. So, let's see. So our current, what do we use for delta Q? Mm-hmm. That's our 880 coulombs that's moving through there in 2,700 seconds. Our current is going to be 0.326 coulombs per second, which is the coulomb per second is the what?
Velocity.
Coulombs per second. What unit is that? Yep,
It's,
the ampere.
is that the same thing as like same games?
Yep. Let me get this out so. Yeah, so things are clearer. Now for part B, what is the drift velocity? Well, you remember
Velocity.
number of electrons times the charge of an electron, the surface area they're flowing through, times the drift velocity. Surface area. And so these electrons are flowing through a wire. What is our surface area going to be? Yeah, so it's a circle. Yeah. We don't have a radius, so I'm just going to do d over 2 squared. So we're going to get 1/4 pi d squared. And I believe, yeah, diameter, we have a diameter. Okay, so your area can be 1/4 pi, and then 2.588 times 10 to the negative third meters squared. Because it gave it to us in millimeters. So when we have millimeters, we can just put 10 to the negative third on there. And so that's going to give us our area. So then our drift velocity, square meters. All right, the number of electrons. That's going to be electrons per cubic meter. Then we have 1.602 coulombs per electron. And then our area, 5.26, 10 to the negative 6 square meters. And then our current is our 0.3259 amps. So your drift velocity, and so again, your amps is your coulombs per second, so you can use that to cancel things out. You end up with 6.67. What?
You did it.
Oh, God damn it. Oh,
It is a Friday, so we are able to do more.
can somebody please DDoS TikTok? No, actually don't. That's illegal. Don't do that. But still, no, it's just
You don't get it.
first off, you have to be pretty good. You have to know what you're doing to DDoS somebody. But It's wishful thinking for TikTok to disappear. It's just not gonna. Well, then take notes.
Take notes on what's up.
Yeah, because the rest of it will be on there. I'll post them, but
Perfect.
so we're talking about Ohm's law, resistance and resistivity. So the main theorem you want to know is your delta V equals IR. R is going to be resistance. So the part of this is that is actually Ohm's law is that delta V is proportional. So it's down here. Delta, so current is proportional to delta V. That's what Ohm's law is. The delta V equals IR works for more than just ohmic materials. Some materials are ohmic, some are not. But delta V equals IR works across the entire span of materials. But we need to kind of figure out what resistance is. Okay, so let's revisit. We remember that our current in E area, drift velocity. We also remember that our delta V, I hope you remember this. E times what?
See,
Nope. E times distance. In this case, we're looking at a material of a length L. So your electric field is going to be delta V over the length of the material. Now the force of an electron through that material this is the one you guys didn't use on your exam that made one of the questions much, much harder.
oh, it's,
Yeah,
few times up.
QE. Because you had all solved for E, but then you went back through and solved all the vectors again for force. Yeah, but it still works. So in this case, for an electron, it's going to be E times E. We also know that force, according to Isaac Newton, is mass times acceleration, where m is the mass mass of an electron. So we can say mass of an electron times A is E times the electric field. The acceleration of an electron in this material is going to be E over the mass of an electron. So let's get a generalized expression for drift velocity. Velocity is going to be acceleration times what? Think of units. Acceleration is meters per second squared. Velocity is meters per second. What's a generalized expression for velocity?
Right.
What are the units of velocity?
Unit per second?
What are the units of acceleration? That'll give me meters per second cubed. Yep. Okay, so, but we have an expression for acceleration. So that's going to be E over the mass of an electron, delta T. Now we're going to go back to our expression for current. Let's see. Did I miss an? Let's see. Okay. So what I'm going to do then is rearrange this in E squared A delta T over the mass of the electron times the electric field. What was our electric field? Yep.
You are. Why?
Oh, just wait. Mm-hmm. All right. So I want to isolate delta V. Remember, that's I on that side. And so then if I divide through, this fraction flips upside down. Times I. Yeah, we just divided through. So I mean you can, it'll be harder to see what we're going to compare it to. Because what do we remember? IR. So now we have an expression for resistance.
Resistance is it's metal divided by mass.
No, no, absolutely not. And that would be neat. The bottom is neat.
Metal divided by.
But we saw up top that R also equals this weird rho over L times L over A. No. Well, if you want to do it that way, yes, you could set them equally to each other and get rid of L. Or you can compare them. What you end up with is this fun little thing here, rho. It's going to be the mass of the electron divided by the number of electrons times the square of the electron charge times delta T. Now, the reason this is important is rho is a factor called resistivity. Resistivity is unique to materials. What does that tell you? It does. So if I give you a problem with that needs resistivity, how do you figure it out? You look it up. You look it up. Yeah, resistivity is going to be unique to the material you're using.
Well,
Yep.
you just look what the resistivity of the wire.
Mm-hmm. Now there might have to be some comparisons because it's also temperature dependent. That's what, okay, I'm gonna guess this is a no, but do you remember in Gen Chem? So like we talked about materials called semiconductors. So how do you turn a semiconductor into a conductor?
Takes temperature.
You heat it up. So when it's at room temperature, it has a set resistivity. And that's going to dictate the resistance of the material. But what happens as you heat the material up? We just said heating up a semiconductor turns it into a what? Conductor. So what happens to the resistance based off the temperature dependence of the resistivity as you heat it up? Huh? It decreases. You get to a certain temperature and the resistance drops to almost zero. And your electrons jump from conduction, valence band to conduction band.
Is there like a hot wire in my basement? It was cherry red, like.
Oh, you were able to see, I was like, did you grab a live wire?
No,
Did
no,
you?
no, no. We were, so our refrigerator went out, so I was going down to the breaking box. And I was looking through the wires and stuff like that, whatever, and I turned it on and off, trying to figure out why our refrigerator was on. And then I looked up, and there was this wire, and it is like a bright red. And I so wanted to touch it, and I'm like, I'm not gonna touch it. So we had to call the electrician, and
Oh, at least you didn't grab it.
no, I wasn't.
Not high.
Yeah, but just think if that would hurt, something like that. The resistivity of that wire was very low. So it got heated up.
So smart.
I don't know.
I'm there, but there are people who would have gone, what's that? And grabbed it.
It scared me because it was like buzzing and really red.
Yeah, that's not a good thing. That is not a good thing.
I was like, wow, thinking for conflict in football, like, you know, where-
Most of the time, that buzzing is electrons escaping the wire.
yeah, that's probably what's happening. But now our fridge works, so, and the wire's not red.
Do yourself a favor, tell your landlord.
Oh,
Okay,
yeah.
okay, good. Because that's a problem that can come back. Okay, so
I think I moved it out in like 2 weeks.
if it doesn't burn down before then,
Or we check every week. It's been fine, they usually replace things.
okay. Now, you notice I've given you very little space to solve this problem. I want you to try to solve it for a few minutes. So let's see. You have a tungsten light bulb filament. So in the textbook, you have a nice little table. Your resistivity for tungsten at 20 Celsius have fun with that unit. Ohms. Yeah. So here's the fun thing about ohms is sometimes scientists do have a sense of humor. And so there's another property of materials called conductance. And so this is ohms, OHMS. What do you think? What do you think conductance is? Mohs. What do you think the symbol is? They just turn the omega upside down.
That's so sweet.
I actually learned that one from Dr. Keith. I didn't know that. I was like, you're kidding me. And I looked it up. No, it's not. He's serious. The opposite of resistivity is conductivity, and it's in mohs.
That's 1.5 diameter.
Okay. What?
Resin. Resin. And you know, resin,
No.
then us.
That means a material has properties of a resin.
What's a resin? I know it. It's like.
Yeah. It's just gonna go certain properties. Yes. Well, that's odd. Resistivity is is part of resistance. So the resistance of a material is material resistivity, inherent resistivity. Multiplied by the length of the material over the area of the material. Is that right? Or did I get that upside down? Yeah, it's L over A. Oh, I have something fun to try this weekend. Little conspiracy theory. Who's seen the old Disney Alice in Wonderland?
What?
Who's seen the old Disney Alice in Wonderland? So conspiracy theory, when she fell in the rabbit hole and fell down like 15, 20 feet, she actually broke her neck. And all of Wonderland was her last moments of life and hallucination.
That's pretty.
Like the Cheshire Cat is her neuron time. So when it fades out.
Since they're all kind of like connected to a certain type of like syndrome and Stockholm syndrome is.
I've heard that.
Like each one has like a different one.
Also, if you haven't done it yet, sometime watch Frankenweenie, Corpse Bride, and Nightmare Before Christmas.
They're all.
It's the same person. The kid in Frankenweenie is the groom, and Corpse Bride becomes Jack Skellington.
The dog is the
Mm-hmm.
dog. What's the unit for?
Oh.
Is it just?
Mhm.
Is it perhaps a number that's close to 7, but more closer to 7?
Yes. Very.
6.9.
Yep.
You use the models.
See, you guys were stretching on that one. There's not a 7 in that number.
Oh, well, there's 6.875.
Yeah, you're reaching. You're dragging your toe trying to keep this play in bounds.
That was such a good sports reference ever. That was so bad.
Now that I know what gives you the ick, guess what we're gonna do? All righty. So we're using the equation. So we need A.
Hey, I've heard, is that your TI 84 on this?
Nope.
There you go.
So remember, we figured this out earlier. The area of this circular cross section is 1/4 pi d squared.
Thank you.
Let's see our diameter. Okay, so that's going to be 0.020, 10 to the negative third meters. The area is going to be 3.14 times 10 to the negative 10th square meters. So now our resistance your length 0.040 meters, 3.14 to the negative 10th square meters, and I end up with 6.88 or 6.90, whatever, ohms. So far, not so bad.
I'd actually name it. I'm like so sad to talk to you about it last week.
You lost one of Eva's. When did you start hating Eva?
Along freshman year.
Okay.
Let's make it into that one. No, maybe. Russian.
No, I'm number one, so I don't.
Oh.
Not today, but I'm thinking, that doesn't matter.
Oh, wow. Okay, go for it. But so I would try just the resistivity of the metal. Most of the standards are going to be at 20 degrees Celsius. Yeah, so that's why we have our next equation, the temperature dependence of resistivity. So let's say you raise the temperature, your new resistivity will be your original resistivity, which is usually your constant at 20 Celsius. So if you look at, again, the table in your textbook, you'll see this list of alphas next to the materials. So you'll have a column of resistivities, a column of resistivity constants.
But there's very-
So let's do an easy one first.
This person.
Actually, here's a question. What would you guess? How many amps passing through your heart is the beginning of the lethal dose? Ten amps would cause your heart to explode. Mm.
0.5.
0.5 milliamps. You were very close, yeah. Yep. 0.5 milliamps. That is the beginning of the lethal scale. So you can imagine how easy it is to electrocute yourself. You can find 0.5 milliamps almost everywhere. So this wire here is carrying 150 amps. You do not want to be the dude touching this wire.
What's the third guy?
Okay, so a couple of things. First off, so if for the first thing, it depends on the length of the wire, remember?
Yeah.
So if you grab the wire, you have like feet or like almost a meter. You have a bird has like this much space.
What if I like hold on my 2 fingers?
Well, there's also the problem of grounding. Also, keep in mind, birds are high enough up and their bodies are small enough, they're not grounding. That's why you see the guys walking the power lines. That's why they don't die. Because they're way up there. So you can find some videos on YouTube. You can see linemen with their gloves and they have like electricity sparking to their gloves. But it doesn't kill them because they don't ground. If they got close enough to the ground, yeah, they would be fried. But first off, the fall is high enough that would kill him on its own. Second off, that sounded kind of wishful. Don't think that about your brother. Third, he would, by the time he hit the ground, he'd be far enough separated from the wire. The electricity wouldn't ground. Well, that probably hurt. So, all right. So let's see if we can figure this out. What is the potential difference between the bird's feet? Because again, remember potential difference across the material is what causes current. So the line itself has a current, but what would the current through the bird be? So we're going to start here. I'm going to replace R with rho L over A. Now, let's see, the wire is aluminum. So we get our resistivity of our aluminum. All right, we need the area of that wire, the cross-sectional area. Let's see, let's just actually put that all into the equation. Okay, so that means our delta V is now going to be I rho L over 1/4 pi d squared. So that is going to give us 4 I rho L over pi d squared. And now we can plug everything in. No, unless I tell you otherwise. If I will, yeah, because sometimes I'll tell you, get here first, then plug in numbers. Otherwise, no, I don't care. See, the one thing I don't expect from students that sometimes is expected of me is I don't expect you to have a crystal ball to be able to read my mind. If you're building it, it's technology and it's not a crystal ball. So find what? I wouldn't mess with that. That's witchcraft. I'd leave it alone. They don't burn.
Oh,
Oh, it's 150. 150 amps. Let's see, our row 2.65. -1/8 ohm meters. Let's see, the length 0.020 meters over pi. Yep. 0.020 meters squared. So your delta V (2.5) times 10 to the -4th amp ohms. We haven't used that unit yet. What is the amp ohm? It has to be volts. It's potential. Yes.